All right, guys, I'm going to go over the Unit 8 study guide for the Part 1 section of the test, which is questions 1 through 23. So let me share. This is what the study guide looks like, and you'll see where it says Part 1, which is for sections 1 through 4 of the Unit 8 notes, okay? And that test will be on Thursday, the 22nd. Okay, let's get my annotated tool up. All right, so how are boiling points affected by the IMFs? Remember, IMF stands for intermolecular forces, and those are the forces that will hold molecules together. So just know that when you have stronger IMFs, that's going to be higher boiling points. Okay, and the reason being is you're trying to turn that liquid into a vapor, which means you're trying to pull the molecules away from each other. And so the stronger the IMF, the harder it will be to break apart. So you're going to have to apply a lot more energy or a lot more heat. Okay, and then of course, if you have weaker IMFs, then you're going to have lower boiling points because it's not going to take as much energy to cause those molecules to separate and turn into a gas. All right, number 2, what causes water to have such a high specific heat capacity? It is the hydrogen bonds. Okay, if you go back and look in your notes, we said hydrogen bonds was the strongest IMF, or intermolecular force. Okay. All right, now the number 3 says discuss the strengths of IMFs related to solids, liquids, and gases. So if we write out here, we got our solids, we got our liquids, and we got our gases. Remember with solids, you have a solid shape, you got the molecules that are very close together. So that is going to have a higher intermolecular force than liquids, and of course, liquids would be higher than gases. Remember, the gases have the weakest IMFs. Remember, gases are all over the place. They're already separated and bouncing around. And then solids will have the strongest, basically, when they're in the solid state. All right, and then bond strength is the same way. Think about bonds, okay? The stronger the bond, it's going to be kind of the same way as those IMFs. They're going to be harder to pull apart, which means you're going to have to add more energy or more heat to get the molecules to go from one phase to the next. So BP is boiling point, and I just wrote out melting point, but anyway. And then, of course, the weaker bonds are going to have lower, because they don't need as much energy to break those bonds, lower boiling points and melting points. Okay, so stronger bonds, you got to apply more energy to get it to boil or to melt. And the weaker the bonds, you don't need as much energy, so the boiling and melting points are lower. Okay. I'll move this up. Oops, not that far. That really skipped. Okay, so here, number 5, we're looking at these potential energy diagrams. And in the notes, you'll see pictures where I have labeled these for you. Okay, so let's take a look at letter A here, or A graph. Look at your reactants versus your products. So the first thing says include information about energy of the reactant. So reactant potential energy is lower. And potential energy, we are just going to abbreviate PE. Lower than product potential energy. Again, PE is potential energy. All right, it says, what is the value of our delta H? Okay, in this case, it's going to have a positive delta H, and it is an endothermic reaction. Because you got heat being absorbed there at the end. Okay, versus, let's compare this to our other reaction graph here. Look how the reactants are higher than the products. So reactants, potential energy higher than product potential energy. Okay, in this case, you're going to have a negative delta H because look, the energy has been released because your product is lower. So if the energy has been given off, it's an exothermic reaction. Like the energy is exiting the system. Clear now. Okay, moving on. Number 6 is, which law of thermodynamics states that absolute zero, which is 0 Kelvin, that should say the movement of molecules, guys. This should say molecules. Movement of molecules stops. And that is the third law of thermodynamics. All right, number 7, how many calories are required to raise the temperature of, we have 207 grams of water from 19 degrees Celsius to 47. All right, now this one, you're going to be using the energy formula. You got the final temperature minus the initial temperature. I've given you, this is M. Remember, M stands for the amount. Here are your temperatures. The only thing I haven't given you is C, which is your heat capacity. Now, I'll give it to you on the test. This would be one of the things that you almost have to memorize if you were in regular school, but this was in the notes too. So when we did the Jamboard, I told my group to go to the Jamboard, and I'm sorry, the Jamboard group that had this question had to go to the notes and look it up. But anyway, I will give it to you. For water, its specific heat here is 4.18 joules per gram degree Celsius. All right, so it says how many calories. So that is a unit of energy, so that's Q. We don't know what Q is. And let's make sure our units match. We have grams and grams, so that's good. We don't have to convert anything for this one. So M is 207 grams. Heat capacity is 4.18 joules per gram degree Celsius. And then for our temperature, the final temperature is 47 degrees Celsius minus 19 degrees Celsius. All right. Keep in mind, your units will cancel. You can get rid of your temperature units. We get rid of our mass units, and it's going to leave us with joules, which is what we want because we're looking for we're looking for energy, but look what it says. It says they want calories. So we're going to have to convert the calories in the end. But anyway, let's get to that first. All right, so Q, if you do the math, you can put this in the calculator first just to get what it is. That's 28 degrees when you do the subtracting. Okay, and you multiply 207 times 4.18, and then by 28 degrees Celsius, you are going to end up with 24,227 point, and you can round this if you want, joules, but remember they want it in calories. So we got to use our conversion factor. This is in the notes as well. Remember, 1 calorie is equal to 4.18 joules. So we've got to convert this to calories. 1 calorie That means your joules will cancel out. So basically 24,227.28 divided by 4.18. And you're going to end up with 5,796 calories for that one. That's your final answer. Okay, so again, like we did with stoichiometry, this one is easy when you're plugging in, but then you got to make sure you end up with the units that it asks for. Okay. Move this up a little. All right, so now we got a calories to joules problem. Okay, so they give us 865 calories, and they want us to convert it to joules. So our conversion factor, remember, 4.18 calories. I'm sorry, 4.18 joules to every 1 calorie. All right, so we want calories to cancel. So the calories goes on the bottom of the second fraction, and we want it in joules, so that goes on the top. And remember, that allows us to cancel out calories and leaves us with the unit that we want. So 865 times 4.18, 3,615.7. You could also just round that to 3,616 if you wanted to. All right, now entropy in number 9, remember entropy is the delta S, and it is a measure of chaos or randomness in a system. Okay, so it's asking us to, look at the phases. So we have solid, liquid, and gas. Okay, remember solids are pretty, set. They have a solid shape. The molecules aren't moving very much. They're very compact. So not a lot of movement going on there. So when we look at our entropy, solids are going to have less than liquids, and liquids are going to have less than gases. Remember that you're going to have the least amount of entropy with the solids. But remember, gases are all over the place. So you're going to have the most chaos, most randomness, most movement of those molecules with a gas. Okay, number 10 is a converting our temperature. So we're going from 48 degrees Celsius, and they want it in Kelvin. Okay, so anytime we go from Celsius to Kelvin, we have to add that 273. So this answer is 321 Kelvin. Okay, it's always the same number. You're adding or subtracting, but remember, if we reversed it and we started with Kelvin and we wanted to go to Celsius, you would subtract the 273. Remember, Kelvin has got really large numbers when you're looking at temperatures. So if you kind of remember how Kelvin is the oddball, we don't, y'all probably haven't even seen Kelvin before outside of chemistry. So, and Celsius, if you think about 0 degrees Celsius and body temperature in Celsius is like 37 degrees. Celsius tends to have lower numbers than what we're used to, and Kelvin tends to have higher numbers. So anyway, Kelvin is the one you're going to, when you have Celsius, you add 273, and you want to go from Celsius. I'm sorry, when you would want to go from Kelvin to Celsius, you subtract 273. All right. For this next one, during a phase change, so when we're going from solid to liquid or liquid to gas, or the other way around, from gas to liquid or liquid to solid, what happens to the amount of energy? And in this case, I want you to think is energy as in temperature. With the process, I remember we said temperature / energy remains constant, which we're going to show you on the next graph. But that's because all the energy goes into breaking or forming those intermolecular bonds between the molecules instead of increasing the kinetic energy. Okay, so it's going into, you know, making or breaking those bonds, basically, intermolecular forces and stuff. Okay, so this is what we're looking at here. This is a graph that's showing you these phase changes. So that was part of one of your homework assignments. So in other words, like right here between this line and this line, this is a solid. And between 3 and 4 here, this is a liquid. And you can see with these, and then from here to here is a gas. The temperature is increasing because while it's in that state, it can actually absorb energy. Now these flat lines here, this is during the phase change. And remember, we just said the temperature remains constant during a phase change. So if you're moving this way, going from a solid to a liquid, you're melting. Okay, and up here, if you are going from a liquid to a gas, you're vaporizing, vaporization. All right, now we can look at this going the other direction. If we're going from a gas to a liquid, this is condensation, you're condensing. Or if you're going from a liquid to a solid, you're freezing. So it just depends on which direction you're going on the graph. Okay, so letter A says between 2 and 3, when energy has been increasing, so we're moving up the graph here, increasing in energy. That would be melting. Okay. And if I can get this to move up. Okay, so between 4 and 5, that's where you're going to be vaporizing because that's showing as you're increasing the temperature. Vaporizing, if I could spell, hold on. Vaporizing. Come on. There you go. That's when you get to that boiling, which most of y'all know it is boiling, but it is turning into a vapor. All right, between 3 and 2, now this one's saying as the energy is being lost, so we're going the opposite direction. So that's freezing, liquid to a solid. And the number between 5 and 4, and again, energy is being lost, so it's reducing in temperature. That should actually say between 5 and 6. So that's when it's going from the gas to the liquid, so that's condensing. Okay, so this was the homework, actually last night's homework, or was due last night anyway. When you guys had one of these graphs you had to label and answer questions about. All right, next one, number 13, heat of fusion. So that's telling you right now it's one of the phase change. So y'all are going to be using the Q is equal to M with the delta H phase change. In this case, their phase change is heat of fusion, which they're giving it to you. And they want to know how much energy, so we're looking for Q. And we're melting, okay? So that's when you go from heat of fusion is solid to liquid. All right, so anyway, we're looking here at M is 8.95 grams. Now, we have a problem because you got to match up your units. We got grams here, but look, we have moles here. So we are going to have to convert 8.95 grams of sodium chloride into moles before we can plug it into the M part of this equation. The 27.95 goes with the delta H, and the 8.95 is the amount. Okay. So NaCl, I'm going to do that up here. NaCl, you got to look at the molar mass. Go to the periodic table, look up sodium, look up chlorine, look at their atomic masses. Sodium's 23, chlorine's 35. Add these together, it's 58 grams per mole. All right, how much did we have? We had 8.95 grams of sodium. And we just said 58 grams per mole. All right, grams cancel. And that's going to leave us with 0.15 moles of NaCl. Okay. All right, so we're looking for Q. We're looking for the energy. We now know that M, at least in moles, is 0.15. And we know our heat of fusion's right here. It's been given to us 27.95 kilojoules per mole. Okay, your moles will cancel. It's going to leave us with kilojoules. All right, and that is going to give you when you put in the calculator, 31 kilojoules of energy is needed to melt 8.95 grams of sodium chloride. Number 14, define specific heat capacity. This is the amount of heat required, I should say required to change the temperature of 1 gram of a substance by 1 degree, and it could be either Celsius or Kelvin. We don't usually use the degree mark with Kelvin, but okay, so change how much heat or energy is required to change the temperature of 1 gram of a substance by 1 degree Celsius. Now, that homework you guys had before where you had to look up the heat capacities, you know, there's a different heat capacity for all substances and actually some of the states too, or the phases. Okay, so which goes with number 15. Actually, I want to show you guys something before. Let me find the notes real quick. I gotta stop sharing. Give me a sec to find my notes because they are not open, and I want to show y'all a slide in the Unit 8 notes that will help explain number 15. Okay. If you were looking up the definition of specific heat capacity, it's on the same slide. I think it's slide 38. Yeah, there we go. All right. All right, so just looking at this slide, there's our definition for specific heat capacity, but this is a table here that just gives some common materials with their specific heat capacities. You see the units are in joules per gram degree Celsius because, again, this is the amount of energy required to raise 1 gram 1 degree Celsius. So that's why we have all the units there. All right, so look at your liquid waters, 4.18. Okay, solid water's 2.11, and water vapor or gas is 2. So you can see that the state or the phase of matter actually affects it as well. But look at water. Let's just look at liquid water compared to, let's say, iron or copper that are metals. All right, 4.18 versus, let's say, copper, 0.38. If you took a piece of copper metal, put it in the sun, and you took a glass of water and put it in the sun, and you measured how long it took for the temperature to rise with both of those, you would note that the metal, pretty much any metal, the temperature is gonna increase a lot faster with the metal than the water will, okay? And that's because these lower heat capacities means it doesn't take as much energy to get that substance to increase by 1 degree Celsius or ever how many degrees Celsius, okay? Where water, it has a higher specific heat. That means it's going to take a lot more heat energy to get the temperature to increase. Okay, you can do a little experiment, take a piece of metal, put it in the sun, put a glass of water next to it, and just keep testing the temperature, and I guarantee you that that metal will get hot a lot faster than the water in your cup. Okay, so that is the answer to that question. Let me go back to our, one second, let me get back to where I was at. There we go. Let me share this with you. All right, so number 15 says to relate higher versus lower heat capacity values to the amount of energy needed to raise the temperature of a substance. So the higher the heat capacity value means the more energy needed to increase its temperature. The lower the value, the less energy needed. To increase the temperature. In other words, the temperature is gonna go up a lot easier if you have a lower heat capacity value, because it's not gonna take that much energy to get the temperature to go up. But if you have a higher heat capacity, then it's gonna take a lot more energy. It's gonna take longer to get the temperature to go up. All right, so let's look at number 16. We are looking at magnesium. Here is our specific heat here. How much heat and energy is given up by a 90-gram sample of magnesium, and here's your temperature. So we're looking at our Q equals MC with our temperature change. All right, let's see, everything matches up. We got grams, so we don't do any conversions. All right, we're looking for heat, so that's our energy, so we need to find Q. M is the amount, so that's 90 grams. C is right here, that's your specific heat, 1.01 joules per gram degree Celsius. And then it says when it cools from 110 degrees to 85. So final temperature on this one is 85 degrees, and we started out with 110 degrees. All right, so guys, make note that for this one, you're gonna end up with a negative temperature because we were decreasing, and it asks how much heat is given up. All right, so now we pretty much, again, just to kind of show you our units canceling, grams cancel, we're gonna be left with joules, and that's what we need because that's an energy unit. All right, so plug it into your calculator, 90 times 1.01 times negative 25. And you're going to end up with a negative answer because it's going to give up 2,272.5 joules of energy as this thing cools down, as the magnesium cools down. All right, number 17, what happens in a container where gas is kept at a constant temperature, but the volume is decreased? Okay, now remember, this is like that picture when we had the container and we had the gas molecules, okay? And then there was like this little piston thing, or compress, whatever you want to call it, is pushed down. So as we push this thing down into the container, what we have done is we've reduced the amount of volume or space that the same amount of molecules, so the pressure is going to increase in there. Pressure increases due to less space in the gas molecules collide. That should not be I should say with, not with. With, oh, come on. With the sides of the container more, which is putting more pressure on the sides of the container. Okay, which is going to cause more pressure. Okay. All right. Number 18 is asking about vapor pressure. All right, so this is the pressure of the vapor resulting from evaporation. So all the little molecules that are able to break away from the surface of the liquid, whatever that liquid or substance might be, in a closed container. Okay. How can you increase the rate of evaporation in an open beaker of water? So now we got an open beaker, and we're talking about rate of evaporation. So that means basically you're vaporizing it. It's going from a liquid to a gas. So that one's pretty easy. You want to increase the rate. Well, what do? You crank up the temperature. Increase the temp. Okay, you want to get stuff to boil, which means it's evaporating, you know, vaporizing. Yeah, crank up the heat. All right, number 20, we're looking at a phase diagram. All right, I'm going to label this first. This is one that's in the notes as well. All right, so we're looking at M over here. This is your solid. When you're here, it's a liquid. Over here is a gas, and you can see you got temperature on the x-axis, and we got pressure. We were looking at this when we were looking at the bell jar experiment. Basically looking how if we don't change the temperature, we change the pressure. So temperature and pressure have a lot to do with, you know, changing the phases. All right, this little point right here is called the critical point, and then you have a point right here is called the triple point. Actually, I don't think we put critical point on this one, but anyway. So this first question says, what phase is compound X, so this is a phase diagram for an unknown compound we call X, in at the following point. So at point M, it's a solid. Between point M and point N, we're right here in the middle, so that's a liquid. And then the next one on your study guide says point N. You can see that that's the gas. You can't really see it, so I'll have to erase this and move it down, but point N is the gas. Okay. Gas. And then it asks you what the triple point is. It's the temp and the pressure at which solid, liquid, and gas can coexist at the same time for that substance. So this is a different pressure and temperature for every substance you're dealing with, but the triple point would be the temperature and the pressure in which all three states of that substance can exist at the same time. Okay, in the notes when we talked about pressure, we talked about 760 millimeters of mercury is also equal to 760 torr, named after Torricelli. And then we said Pascal came along and made up his own unit. So we have kilopascals. And then we said that eventually the whole group of scientists got together and said, we got to come up with one unit that's good for everybody. And that was atmospheres. So those are your conversion factors. So look at what we got. They want us to take 305 kilopascals and turn it into atmospheres. So we're going from kilopascals to atmospheres. We got to put the kilopascals on the bottom. That should say 0.3, by the way. Kilopascals over, I'm sorry, under 1 atmosphere. We do that way so we can get the kilopascals to cancel out because we want to be left with atmospheres. Okay, so 305 divided by 101.3. And when you put that into your calculator, you should end up with 3.01 atmospheres. All right, now we did a lot of looking at pressure. We looked at the bell jar experiment. You saw where we sucked out the air and created a vacuum in there around the beaker of water. And when that was reducing the pressure, and we didn't change the temperature at all. So when we reduced the atmospheric pressure and kept the temperature constant, we got that water to boil. Okay, so you got to reduce the atmospheric pressure. And that will allow, you know, the pressure is going to be let up and it allows those little vapor molecules to break away, a little water or whatever substance. I guess we're using water for this one. Yeah, water will be able to break away from the surface and vaporize. Okay, and that was the last question. Part 2, guys, we will do later. That's not going to be, none of these questions that are 24 on will be on this first part of the test. So you only need to concern yourself with 1 through 23, knowing how to do these conversions and being able to answer these questions and look at these different graphs and be able to interpret them on this part 1 of the Unit 8 test. Okay, so the Unit 8 test will be on Thursday, April 22nd. I need you guys to come to Zoom on time because the test will be scheduled during class time. And you can remain on Zoom after you've checked in if you want to take the test, but you do not have to stay on Zoom to take the test. I just need to check in your attendance. I will stay on Zoom in case you do have questions about the test. But again, test will be Thursday the 22nd during your regularly scheduled class time. All right, guys, email me if you have any questions. Have a great day.